All right, so today we are looking, as it says here, it's very big, velocity time graphs. So velocity time graph. So here's an example of a velocity time graph. Velocity here, time here, and it's got this curvy shape. All right. So yeah, it could be straight, could be curved, whatever. It is, and you need to look at the question as to see what's relevant. Okay, so first of all, for a velocity time graph, the gradient, which of course is dv dt, from what we know about our calculus, our gradient of a curve at a point is the derivative, so dv dt, and of course that is acceleration. So the acceleration is the gradient of that curve at any point. So that's one thing there. And then I've got these A's and these B's here. So, this A, the area, and so again we can use calculus for that, the integral. So for this A here, that would be the integral from 0 to A of whatever the function is, and that will give that area. And there's part B, again with the integral from A to B. Now, because this is below the axis here, you're going to get a negative answer. So if you want to know the distance travelled, you need to make sure that you ignore that negative, so that you get the distances both the areas. Of course, if you're after displacement, then you just use that, because this distance is in the positive direction, this distance is in the negative direction, so it's turned around and it's going back. All right, so okay, so from what we know about the graphs, the relationships between those things, here's that. So the acceleration is the gradient, I've said that. Displacement is given by the signed area bounded by the graph, i.e. A minus B. All right, and so we can just go straight away 0 to B, or not A minus B, A to B. We can just go 0 to B. We don't need to take into account the fact that that bit below is negative, because we're talking about displacement. So where we start to where we finish. So that's taken care of, but the distance, as I said, we need to split it up into two, the bit above, the bit under, and ignore the negative. All right, so I already mentioned that. Okay, so let's have a look at a couple of examples. Here we go. So this is in the textbook, so it's the Cambridge textbook. All right, so car travels from rest, it says here from rest, and what that indicates is at t equals 0, its velocity was rest is 0, okay? Then it travels for 10 seconds with a uniform acceleration until it reaches a speed 90 kilometers per hour. Constant speed for 15 seconds, finally decelerates 5 meters per second. Calculate the distance travelled from start to finish. All right, so before I even go any further, notice here we've got seconds, meters per second squared, but kilometers per hour. So we need to change our 90 kilometers per hour, because we need its units to be the same as the units we've got for these other things, which is meters and seconds. And so I already mentioned this previously in the last, the first video. Divide by 3.6. I don't know why I've put 9.8 there. Let me get rid of that. It's 90 divided by 3.6, and when you do that, you get 25 meters per second. All right, so let's have a look at our velocity time graph. Always a good idea to draw it. All right, so I can put there one at 25. I should put meters per second, and I should put seconds, of course. All right, so it says from rest, that's here, for 10 seconds with uniform acceleration until it reaches a speed. So after 10 seconds here, it reaches this speed. Now, because it says uniform, what it means is that that's a straight line. All right, then travels with this constant speed for 15 seconds. So with this constant speed. So if it's constant speed, it's flat, and that time period that it's for that is 15 seconds, not 15 seconds from the start, but 15 seconds from when it got there. So that's 25. Then finally, it says it decelerates at a uniform 5 meters per second squared until it stops. And what is that time? We don't know, but it says at 5 meters per second squared, so I know that that gradient there is negative, because it's decelerating, -5. All right, so now I've got all the information that I need, but it'd be handy to know what that time was there. So for this last part, what I'm going to do here is I'm going to split that up into there. So for this bit in here, what do I know? I know that for that for that period of time, it starts at 25 meters per second, ends up at 0. The acceleration is -5, and it'd be handy if I knew what that time period was. So if I go v equals u plus at, and then I'll go 0 equals 25 minus 5t, bring the 5t across, and so the time is 5 seconds. So if that's 5 second period in there to there, then this here, where I've got the question mark, that's therefore 30 seconds. All right. So there's now, I've got all information on my graph. It says calculate the distance from start to finish. All right, so you notice I dealt with all of that stuff, filled in the graph before I even got to that. And so distance is what we want to know, and velocity time graphs, the distance is the area. So in this particular case, we can just split it up into triangles and rectangles. So the distance equals the area. And so we've got this triangle here, that one there. So it's a half of the base of that triangle, which is 10 times the height, which is 25, plus this rectangle here. And so I want that length there, which is 15 seconds. And the height, of course, is 25, so 15 times 25. Plus, finally, this triangle over here. And again, that's a half of the base. And the base, that's 5 seconds across there, times the height, which again is 25. All right. Then you stick all of that in your calculator, or do it by hand, and you get 562.5 meters is how far our car has travelled throughout that particular journey. All right. So let's have a look at another one, and this one's a little bit more involved. So you have to take your time with this. All right, so here we are. Lots of words in there. So before I even go in the rest, I'm looking and I'm seeing I've got kilometers per hour, but I've got seconds, kilometers per hour, seconds, kilometers per hour. So I've got to change those numbers to meters per second by dividing by 3.6. So when you divide that one there by 3.6, you get 33.3. This one here, when you divide that by 3.6, you get 27.8. And this one here, when you multiply that by, divide by 3.6, you get 36.1, I believe. All right, so let's have a look. A motorist travelling at a constant speed of 120 when he passes a police officer. All right. There we go. He continues at that speed for 15 seconds. What? Continues at that speed for another 15 seconds before uniformly decelerating to 100. Again, remember, uniformly, straight line, in 5 seconds. So that's another 5, so that's 20. Uniformly decelerating. There we go. And then to that, and then police car, blah, blah, blah. So it doesn't, so that motorist is then going to continue on at that 27.8 meters per second after that. All right, let's get rid of that. And let me change my colour so I can do the policeman. A police car takes off after the motorist the instant he passes. All right, so there's time equals 0. So that instant that the motorcyclist comes past, and it accelerates uniformly for 25 seconds, by which time it's reached 130. 25 seconds. Uniformly. It continues at that speed until it catches the motorist. Yeah, right. So there we go. After how long does the police car catch up to the motorist, and how far has he travelled? So how long, time, how far distance. All right. So let's say, for example, well, not for example, to help us, we can say, the policeman catches the motorist here at this time, big red T. Now, when you think about this kind of thing, the police car catches the motorist. So that statement there, for the police car to have caught the motorist, what that means is, so police catches motorist, what that means is they are in the same place at the same time. so the same place, which if the same place from here is distance. All right, so same distance at same time. Remembering the distance is the area underneath. So if we come up to this point here, you can see because there's more area under the blue than the orange, up to whatever point that is there, the motorist's up ahead somewhere. All right, so what do we know? Let's have a look. So if it's the same distance at the same time, then we need to write some expressions. So let's write some expressions, and I'm going to say x for the motorist. So x for the motorist is the area, so I'm going to break that there, I'm going to break that there. So this rectangle here is 15 times 33.3. Plus this area here, now this shape is a trapezium, and the area of a trapezium, hopefully it's on the formula sheet because it could be handy, but anyway, it's this parallel sides, you call them A and B, and the distance between them we call h, and so it's a half of A plus B, so that's 33.3 plus 27.8 times the height. Now the height's this distance here, which in this case is time, and that's 5 seconds. All right, now up here, this one here, so this is the time big red T where the policeman catches up to our motorist. So we've got to add this bit here. All right, so that's easy enough. That's 27.8. Question is, what's this bit here? Well, this big red T is from the start. So the time period in here is big red T minus 25. And that'll tell us how many seconds in there. All right, so if you multiply those out, expand, collect your like terms, etc., because I've prepared one earlier for the motorist, you get 27.8 T plus 96.25. All right, now I'm going to change to back to my orange. So for my policeman is my orange. So again, the same thing. Now policeman, I break the policeman's down here. And so the policeman's distance is this area there, which is a half of the base, 25 times the height, 36.1. So x for the policeman is a half of that base, which was 25, times that height, which was 36.1. Yes, 36.1. Plus this rectangular bit on the end here. Oh, I've made it. No, I've come to that. This rectangular bit on the end here. Now, I explained that before. Time from the start minus up to here gives us this bit, which is 25. And so it's just 25 times 36.1. Well, not 25, so it's 36.1 times T minus 25. Now, I'll come back to what I just noticed, the error that I made. So that's 30, when you expand, collect your like times 36.1 T minus 451.25. All right, now back to the, I'll just deal with that error that I talked about. That's here. let me go there. I just wrote the wrong thing down. The calculation's correct because I've looked at my notes and I've used the correct thing in my notes. But that shouldn't, of course, be 25 because that area we're talking about is this one all the way here. So the side is this side there, which is t minus 20. All right, so t minus 20 is what should be there, not 25. Whoops, wrote the wrong thing again. Minus 20. There we go. All right. Yeah, so my notes have that written, and so when you expand that, you do get the right thing. All right, so sorry if I confused anyone there. I do apologise about that. So, what do we know? So there's our motorist and our policeman. As we know, when the police catches the motorist, they're in the same place at the same time, and so XM equals X policeman, and so our 27.8t plus 96.25 is equal to 36.1t minus 451.25, and then when you rearrange that sort of stuff, so I'll move that to there. Move that to there. So take 27.8t from both sides, you get 8.3. And then if I add 451.25 to both sides, I get 547.5. And then divide by 8.3, you get 65.96 seconds after the motorist passed the policeman. Does the policeman catch up? We want to know how far, so we can just use one of their expressions. And so that was 27 for the motorist, 27.8t, and t is 65.96. And then we add 96.25 to that. And so 1930 meters is how far they have travelled. All right, so take a bit of care with these velocity time graphs, thinking through, first of all, setting them up, and then the areas and things like that. All right, if you're not sure about anything, make sure you get help, and as always, have fun.